So let's have a go at the module 2 analytical methods and separation techniques. So a solution of potassium manganate, right, is standardized by titration against the primary standard ethendioic acid. The standard solution of potassium manganate is used to determine the percentage of iron Fe2 plus in compound R. List three characteristics of ethendioic acid that make it a suitable primary standard. Characteristics of primary standards, let's go.
This table too, I'd say.
Okay, so it has high atmospheric stability, right? Stability. All right, what else?
Able to obtain high purity.
High purity. Able to be obtained in high purity. Anything else?
So it being, yeah, soluble in water. Somebody said it.
High solubility, lovely. Right? Relatively high mass. Right? Atomic mass, actually. Molecular. That's the atomic mass for a molecule. Oh boy, I should just resign right now. Okay, there it is. Lovely. Now, in preparing the solution of ethendioic acid for titration against manganate solution, two pieces of laboratory apparatus with a high degree of accuracy are required. Name these two pieces of apparatus. High degree of accuracy, please. So let's go.
A burette.
Mass balance.
Wait.
Pipette.
Okay, hold on. What we're doing, we're preparing the solution of ethendioic acid, for the titration. We're not going to be beating anything. The pipette and the volumetric flask will be the first options that should come to mind. Have you guys done this in labs already? Because I'm asking, because once you do it in labs, you should be able to say, okay, I used this for that, right? I've done this before. So if we haven't done it, then I understand where the issues would come from for this question. But this question really, you kind of have to know experimentally what to do. And hopefully we've done the experiment, right? I would remember the answers for these because I have labs every single week, 3 labs a week. So stuff like that, right? So we prepare primary standards all the time. We standardize all the time and stuff like that, right? So generally we use the pipette in order to measure specifically the volume that we're going to be using, right, in order to mix into our volumetric flask, right? 25 centimeter cubes of aqueous solution of R requires 24.80 centimeter cubes of 0.02 mole per dm cube per manganate, right, for a complete reaction. The equation is here. Calculate each of the following: the number of moles of permanganate used. How do we do that? Go ahead. What is it that we use? Guys, is that more question? No. Well, a titration question? No. How do you do this? No. Go ahead.
So, so the First thing you would do is write out your formula, which is mole equal concentration over volume.
Okay, let me follow what you're saying. So mole equal concentration divided by the volume. All right. Okay.
And then you can plug in your value because that gives me the volume and concentration for the magnet. So,
Manganate. Mm-hmm.
yes, the magnet, right? So it can be 0.02 mole per dm cube over 24.8 over 1000.
There's a division sign on the keyboard, right? Like I'm here looking for a division sign. All right. There's not a division sign on the keyboard. I didn't know that. Okay. Divide that by 1,000, and let's use brackets to show the difference. All right. So who agrees with this? Do we agree with this?
0.8.
Do we all agree with this? Does this make sense to you guys?
Sir,
Okay, go ahead.
I believe
Yep.
I believe it's concentration times volume multiplication.
Hmm. Concentration times volume. All right. So is it concentration times volume or is it concentration divided by volume? Hello? Nobody wants to challenge that? Is that true? If concentration is the number of moles in, okay, so let's clear that up. So if the concentration, the molar concentration is the number of moles divided by the volume, right? Then what is mole?
Concentration over volume.
Concentration over volume. All right. So Danik, is that fine?
Because if
Yes,
you
sir.
do the
Okay.
formula with your technique, then you get in 460.
All right. So 0.202, right, will be divided. Give me one moment. All right, so now I can see everything. So we're gonna have 0.02 and we're dividing it by the 24.80 divided by 1,000. What is the value that you're getting?
0.8.
Mole per dm cube? That's an interesting value. All right. Mole per dm cube. All right. So we have that there. If we have that there now, the next question asks us the number of moles of iron in the 25 centimeter cubes of aqueous R. So we'll get the number of moles of iron. Go ahead.
we put in more for DMQ?
Oh, my bad. I need to put the mole. Sorry about that. All right. So in mole. Okay. So how do we find the number of iron now? The number of moles of iron. Let me go and check something really important because they have two different ions.
Sir, you use the mole.
So we use the mole ratio. Right? So if manganese is 0.8 moles and we need 5 moles of iron to react with 1 mole of manganese, then what will be the calculation here?
You have to convert CMQ to DMQ and then cross multiply.
And that would just be this divided by 0.025.
Yeah, basically.
And that would be
Sir, 0.0184. Or you could like make it exponential.
okay, so give me one moment. Let me figure out what that makes. Okay.
Sorry, sir. No. Sorry, wrong. Sorry. It would be 0.01984. But you could make it exponential.
Okay, 0.01984. Alright, so I think that was generally the issue was happening because I was right. I was going through the question, right? And the answer here seemed quite right. So let's see what's happening here. So if the mass of the copper is not the copper, the iron is gonna be this one. 0.01984, right? And we times that by 55.8. What are we supposed to get? 1.107, right? Grams.
Yes. Yeah, that's what I have.
And now this specifically should be the 1. Oh no, that's wrong. 1.107, right? And that would be divided by the mass concentration, which is at 40.90. Which would give us 0.027, right? And then this would be mass, that would be that, so this would be that, okay? And then what we do now is times it by 100, right?
Yes, sir. So it's 2.71%.
So it would be equal to 2.71%, right? So what was happening here? I was getting really confused as to where the things are, but the answer, the original answer from 3 going down would have allowed me to be correct. What happened here, right? Forgot to use this value down there, and that's why I would expect so much time to do that one question. This should be here. I wrote it in the wrong place. Is that what you're saying?
Yes, sir. Exactly. Now for the number 3, that's the